and I'm pleased to be here. And so what I'm going to talk about is our journey from where we've been last couple of years into the last year, what we have done. And as said, King, we have been around since 2003, made over 200 games, and we're around 1,800 people. And we have 13 studios around the world, one in Seattle. And we have roughly 463 million users per month that plays our games. And we got acquired by Activision Blizzard February this year. So now I think we are over 500 million players that we have to cater for. So we have built some successful franchise games, and the most known are Candy Crush. And the QA department at King has exploded, I would say. Today we are around 150 to 200 QA engineers. And we have different types of engineers that cater for the game teams. So the game teams, they own the quality of their games. So what we have done is that we have like a pool of different types of testers that they can add to the team depending on their needs. So I work as an agile testing lead. So we are more like a traditional test lead. But what we have done is that we have changed the traditional way of how test leads work into more like a QA coaching role. So what we do are that we are planning the test work, and most of the time we are working together with the developers, coaching them into have a QA mindset when they do the development work. Another thing that we have are what we call ninjas, and those are exploratory testers. We have those that sits embedded in the teams, and we have a pool of ninjas that teams can borrow in when they have needs for releases. And those ninjas, they are sitting, they're pair testing with the developers. So the developer develops a function, and then he gives it to the ninja to try it out and give him some kind of instant feedback on the progress of the function. Another role that are available are test automation engineers. Historically, I'm not sure how many of you have done the test automation route. The idea was that they should be like trying to automate everything that we're testing manually. But there are like practical challenges to that. Normally, it's not enough to have one person that's supposed to like keep up with the new functionalities that is being developed. We're working usually in 1 to 2 week sprints, where we spend like 1 week developing new functionality, and the week after we try to test them. So it's like, a challenge to automate that at the same pace. So they're usually behind. And what we have done now are that the test automators are more like the agile testing leads. They're more coaching the developers to do the automation work themselves. And then we have the data scientists, and what they're doing are that we're like a data-driven company. So we generate a lot of data about how our players are playing our games. And the data scientists, they're evaluating that data, that it's not polluted, and also that it aligns with the business objectives that we have in the company. So what they do in the game team, is that they are like driving what features we should develop and not, which one we should kill and which one we should, emphasize on. And then we have the developers, and their role has changed drastically from just definition of done being like outputting some kind of functionality. Now they have to test what they deliver. That's if they have not tested, then they can't move on to the next feature to implement. They need to finish testing the feature that they built. So usually what they do is that they either write some kind of unit tests and let the Ninja test it through, or they test them themselves manually and see that things works. And as an example, Candy Crush has over 2,000 levels, and we release in 2 weeks cycles. So moving on forward, it's not sustainable to test all of this manually or try to have techniques to automate this where there are a lot of manual maintenance work needed. So what we have done is that we have been looking at, okay, what alternatives are out there? What are the next things that we could utilize to improve the game development process? And what we have started to look at is artificial intelligence. As you might know, it has been around a long time, plus 20 years, I would say, in the public eye. An example over here is the Deep Blue that beat the world champion in chess. And then this year recent, the Google AlphaGo that beat the best Go player in the world. So we've been looking into that area and those programs or bots that they're using. We looked at what is a bot. We tried to dissect it and see like, what is it doing? And the focus for the bot is to automate whatever task you want to, make more efficient. And why do we need them? Why do we want them into our development process? The hypothesis that we have had is that it could help the level designers to cope with the huge amount of levels that they create. We need to, like, in some way, keep the quality of the levels on a high level, because if we don't do that, the players will get tired and play other games. And from a QA perspective, it's been interesting to see if we can find areas where the bot can help us to reduce or speed up the QA work. And data scientists, they're interested in like how can we explore all of the data that we generate with help of the bots. So that was like the input to going into looking into this area. And what we have done initially is that game teams, they've made their own bots, simple ones that plays the games randomly with the purpose of just finishing the level as fast as possible. So, and the reason we've done that is to, for each level that we produce, we need to prove that you can finish the level. So there are like illegal requirements for that reason. But those bots has been, they've been really good at doing one specific thing. They've been like hard-coded to do, the only thing is to finish the level. So they're not aware of what they're doing. They're just, in a predestinate way, playing through the level. And the learnings from doing that is that there's a maintenance baggage that comes along if you have a bot that works like that. So what the bot does, it does it really well, the thing that you have hard-coded it. But the problem are that if the functionality changes, you need to have someone that maintain that bot and update that the directives that the bot should use. So we've been like thinking, okay, how can we take this bot to the next level? What more is out there? So what we were thinking of, like, okay, how can we update this bot so it works more generic over different games and not just that you have to have one bot for a specific game, but the bot should be able to run multiple games. And how can it cope with the complex features that are added constantly so that bot creators don't have to maintain it manually all the time. And also like how can we make this process more automated? So what we have come up with, there's a algorithm that's called Monte Carlo tree search. So what this algorithm does is that it iterates through all of the combinations that you have in your program. So at a given state, you are looking at all of the possible moves that you have, and then it plays through all of these moves. And what it does is that it first selects a move randomly, and then it steps down into that move and looks what other sub-moves can I do. And then it does one of those moves and plays through the level to it's either finish the level or fails the level. And depending on that result, it saves that play out. You get like a score. Okay, was this score successful or not? And over time, what you can do is that you can, as an example here, if you have different options, today, if you use this heuristic bot, it doesn't know which of these options has the highest probability to be successful. But with the Monte Carlo tree search, what you can do is that you can go through all of the alternatives that you have and get like a ranking, which of these moves has the highest probability to be successful. So what it does then are like, in the first step, you get the move to the left here, 36%. That one has the highest probability to be successful. So you play that move, and then you look at the next move and see which one of those moves have the highest probability to be successful. And then you pick that, and then you do that until you complete the level. And this is how it, question?
Can I ask, you mean it does that in memory before it makes a move, not makes moves and then rewinds the game, right?
It makes a move randomly, and then it plays it through the whole way, and then it rewinds itself and to the same state where it was when it selected a move, and then it looks at the other moves that are available, and then it plays out that path also. And you can see that in this diagram here, where the inner circle here, you start with the move number 1, and here you have different options where it can go. So then it picks one of these and gets to the next sub-level. And then it does that for all of the options that it has on each level. So after, like, in this case, 300 iterations, you get something like this. And here is like an animation of it running. So the green one are like successful playouts, and the red ones are failed playouts. So you can get like for a level, you can get like an idea of, you can map out the playout that you can later on use when you do the playout to see, okay, which of those moves has the highest probability to be successful. Right? So we've done this, and when we have run it on a bunch of levels, what we have, our takeaways has been, in this graph here, you can see in the middle we have this grade line in the middle. That represents when we design a level, we have like, we set like a target criteria for completing the level. So as an example, we might create a level and say that you have 25 moves to complete this level. So if a player plays a level and completes it around 25 moves, then that's a good estimate from our side in the playout. So in this graph here, what you can see here is that the top, the orange graph, it represents the heuristic bot, the one that are hard-coded. And that one usually has a tendency to underperform because it doesn't handle different combinations, variations that good. The Monte Carlo tree search version of the bot handles it better depending on how many iterations you're running on a level. So the more simulations you run on it, the better it becomes to predict, because it knows the scores of the playouts better than just playing it through randomly without any notion about the playout. And at the bottom, we have the human players playout. And they have a tendency to overperform because they learn the levels, how to complete them. So they are like a little bit cheating, I would say, because they know, this level, with this strategy, I can complete it much faster than without don't knowing anything about the level when you start it. All right, so the takeaways from doing this Monte Carlo tree search was that it's closer to the playouts that we do with that are closer to the expected playout that we have. It's better than the heuristic that are playing it randomly. So that's really good. And it's quite easy to tune it, to tweak it, the bot, depending on the learnings that you get. You can set different exit criteria, like how many simulations do you want to run, and what weights should every decision have. So then you can control a little bit how you want it to play out, depending on what type of learning that you wanna look into. Another learning was that it's time consuming. One level takes around 5 to 10 minutes to play through. So that's something that you need to take into account when doing this, especially if you have 2,000 levels. So then we were like, okay, this is a good start. So how can we take this further? What more is out there to do? So what we found was something called NEAT, Neuroevolution of Augmented Topologies. So what that is, it's like a artificial neural network algorithm. And what that algorithm does is that it mimics our way of learning. So what it does an action, it learns what it did, and then it evolves. And our hopes with this algorithm was that it could help us in increasing the playout to be more guided, more that it behaves like a human when it plays. So before, when we have the playouts, each of the different functions, the bot were not aware that if you combine them, you can have a different playout. So it just pick one of the functions and just does that one until it finished the level. But with this NEAT functionality, what you can do is that you can create multiple bots that have different submissions, and then you let them play through the levels, and then you pick the best one, the ones that perform the best, and then you breed them together and get a new generation that takes into account what each of the first ones had as an initial emission. So an example are that we create a bunch of bots, one that are focusing, like at the left side here, blockers. So what it is doing is trying to play out the levels using this blockers type. The middle one focus on jellies. Okay, if I play those, how are the play out? And to the right, special candies. You have a bot that are focusing on that. So then you run that a lot of simulations, and you get like the best performing bot for each category, and then you breed them. Then you take the learnings from each bot that are most successful, then you create a new bot. And this super bot or whatever, you do the same thing. So what it looks like, or like in the left side, that's when you have this play out with the Monte Carlo tree search, where it isn't aware of the combinations that it can do. And to the right side, that's after you've done this neat run through, it's aware that it can do a lot of combinations with the different, in this case, candies. So what we do that before we test a level of the bot, we need to train the bot so it learns different functions that it can do. So what we do is that we run the bot on different types of levels, so it are like exposed to different type of functionality. And after we've done that, then we run it on a certain level together with this Monte Carlo research. So this is an example of a neat training of the bot. So what you can see here is the red curve at the top. That shows the score of the best performing bot in an iteration. The yellow line shows the average score of all of the bots in that iteration. The green lines shows the number of bots per iteration. And the blue lines at the right side shows the best scoring bots, neural nodes that it has come up with. So here is how it looks when it runs. And this training takes like 5 to 6 hours. So what we do is that we run it overnight. And what you can see here is the green line, it goes up, and then it spikes down, and it goes up, and it spikes down. And the reason for that is that we have like a criteria. When the bot is not getting better after X number of cycles, then we reset the bot and use the best performing bot as a seed for a new iteration of simulations. So we do that until we have like a criteria when we think, okay, now it isn't improving anymore. And then we take that version of the bot and that play on the level that the level designers creates. So the learnings, takeaways of doing that, combining the Monte Carlo research and the neat algorithm, are that the bot are reaching the goals faster using the neat than without the neat. So you need less simulations to be able to achieve the result that you're looking for. So that's the takeaway. So it isn't. It's marginally better, but it's faster than the Monte Carlo research. The Monte Carlo research algorithm is quite generic, so it's coping very well. But with neat on top of that, you can reduce the time needed to do like a play out. That's the takeaways we have today. But there are different versions of the neat algorithm. So what we're doing now is that we are trying them out to see if if we will come to other learnings with the other versions of the neat algorithm. Another thing that we learned are when we did this bot integration to our games, it's important that the games have support for bots running the game. And that's a challenge that we're facing now, because when we create new games, so this is like a takeaway for you guys. If you're going to try out bots, it's good if you look at your application's design to see if it's able to support a bot using it in an efficient way. So in this graph here, what you can see, the green area represents the time the application needs to play through a simulated play and return the outcome to the bot. And today we have not, when we started this, the game engine was optimized and didn't save the states for each move. So what you can do to reduce the amount of time there, you can, if you save all of the history of a playout on the engine level, you can return that value immediately. You don't have to wait for it to simulate through all of this. So that's one area where you can reduce a lot of time if you're going to work with this. The yellow line shows the neat function, how long time that takes. And that overhead time it's marginal, so that doesn't affect the simulation time. The pink area represents the time it takes to, after a playout, to get back to the state that you were in. And that also, you need to do a simulation play run to first play through it, reverse it, and then get back to the state that you were in, and then from that state pick a new path. And that's also, if it's built into the engine, you can get that result back immediately. So what we're working on now is to get this bot from 5 to 6 hours down to on commit. So when a developer checks in code, the bot should play through the whole new updated functionality within as fast as possible. And desirable for us is under 5 minutes. So the developer will get a feedback within 5 minutes that what he did was, if it was good or bad. And one thing that we're doing now that we're experimenting is with, we're using GPU processing power to try to get down the processing time. And so that's one area where we're looking into. So what does this mean for the level designers? Before the bots, the level design process looked like this. The level designer first create a level, then he gave it to testers. They tested through the levels. And then we have business performance people that look at the results of that play out. And then they give feedback to the level designers. This level is too hard, or it's too easy to complete. So they need to tweak the levels. And then when they've done that, they send it to our users, and they play it. And then the business performance people look at their play out and say, okay, is this level good or bad? And then gives that feedback back to the level designers, and they update the level to reach an optimum level of difficulty. The problem with this whole process, or the challenge, I would say, one is that it takes from days to weeks for this loop to be completed. That's one thing. And another thing is when you play a level the first time, the probability of a player going back to a level to play it isn't as high as it is when he plays it first time. So you need to get it. If you can get it right the first time, that's better for the player experience. So when we applied bot to this, what we have seen is that the level designer creates a bot. The level designer creates a level, and then let the bots play through the level. It takes around 10 minutes. And then he gets instant feedback how the level is performing. So he can do the adjustment. And then when he's done with that, usually it takes 2 or 3 iterations to adjust it correctly. Then he can send it to our end users to play it. And then he's done. And what's happening is that the business performance people are monitoring this because we have started this. This is early days. So we need to build up a confidence level of the bot. But it's looking promising. It's, this process has helped us a lot when it comes to reducing this turnover time. So the takeaways that we have now from the bot are that it helps out a lot when you do the tweaking of the levels. Reduces a lot of time there. Another thing that we're using it for is crash testing. When we have a lot of crashes in a level, we can use the bot to exercise that level to try to figure out what's triggering the crash. Sometimes you have random crashes, so that can be really difficult to iron out. Performance testing, we can measure when the bot plays the levels. What we're looking into now is to measure battery drainage, CPU usage, all that stuff to slimline the game's physical performance. And then regression testing there we're looking at to use it to replace manual time-consuming test cases. So we're going through that now and refactoring a lot of our test suites and replacing them with the bot test cases. And the data scientists, what they're using the bot for is to try out different hypotheses, and now they can get much faster feedback of their hypothesis than before. And the challenges, if you're going to start with a bot initiative that we've learned, is first you need to identify ownership. Who should own the bot? Should it be the team, or should you have an external bot team? Do you have the knowledge and the resources within a team to be able to do this? So that's questions you should ask before you start this. And another challenge are when you do the integration with your application. The bot needs to be run in a non-GUI mode, like headless mode, for speed reasons. And the bot should be able to support different code languages. So if you have like an application in Lua and the bot is written in C++, you need to take that into account. Try to make the bot as code agnostic as possible. And a good way to start this is to have either a hack day or dedicated sprint to do some kind of initial bot, and then evaluate if it bring an added value to your team. And then if you have something like this, if you believe in this, one thing is to think about creating some kind of bot API, so you can reuse the bot for other applications if you have multiple applications in your company. And another thing to think about is maintenance. The bot training takes time, so how can you reduce it, like we're trying now to do it on commit? And you need to think about infrastructure. What type of infrastructure do you need to invest in to be able to do that? And also what of strategy should you have to extend the bot? Should you have like dedicated bot developers, or how should you do that? Yeah, that was what I had to talk about. So, questions?
Okay, so let's start out with, let me get a mic. We have a couple extra minutes for questions, so I'd like to see a bunch of green cards. Okay. $90, 115, 90, 123, 61. That is a flurry indeed. Any more? Okay, let's start with 115.
You said that one of your major goals was to... Thank you.
Thank you. You said that one of your major goals was to bring down the time that it takes these bots to run through new levels. It sounds like it should be very parallelizable. Can you do that just by throwing hardware at it?
Yes, and we are we are looking into that. We're exploring it, but the primary focus now has been just to learn this new technology, the pros and cons with it, and we will get into like an optimization phase when we feel confident what we can get out of this. So we know that there are a lot of areas where we need to look into, like how can we, in a smart way, optimize this. One idea that I have is it would be really cool if we can use the clients, all of our users, to help out with this. Imagine that power.
So this is good for us to see in relation to, 500 million users, in 2,000 levels. With your interactions with others that are trying this type of technology, what other kinds of user-facing applications do you see this being applicable to?
I would say everyone that's using big data, where you are data-driven, I think you should really consider looking into this if you want to stay competitive moving on forward. Because we have started to do that. A lot of other all the big ones are doing it. So if you want to be, current in that race, I think you should, start to look into this. That should be like your, I would say, like a criteria for looking into this.
Could you explain what you meant by breeding the bots in a little more detail?
Can you repeat the question?
Could you explain the breeding of the bots in a little bit more detail?
Okay. What you do is that you do this playout. So you get like a ranking of a playout, and then you have like different sets of playouts with different rankings. So what you do is you take the highest ranked playouts, and then you try a new playout where it picks the paths that the two playouts took. And then depending on that playout, it saves that. So it has like a list of what should be the priority choice for each state that it is in. And then it's like a list where it updates. So you get like a current list of these playouts has the highest probability to be successful. So I'm not sure if you.
How are they bred? Sorry. What criteria goes into deciding which two bots get bred, and how do they go about?
So when you do one simulation, you define like a success criteria. One can be, for one level, it could be like score. This level should score as high as possible. Another could be time, like this bot should complete the level as fast as possible. Another could be like you should do as many, you should trigger as many special functions as possible. So you train it, you do the playout with different focuses, and then you combine the most successful ones, and when it comes to like a playout where it says, here's a candy, and according to my previous playouts, this one has a higher success rate than another one, and then if it sees like 2 or 3 that are like that it knows, these 2 or 3s, if I combine them, it like points in areas where you should focus the playout, if you should summarize it. So it has a lot of different combinations that you can pick from. So what it does, it optimizes, okay, which of these playouts should I pick and play? Because it's like an optimization algorithm, because you don't usually have the time to play all of the combinations that are available. You need to have like these boundaries around the playouts. So the NEAT algorithm and Monte Carlo research, that helps out in like filtering out which move should we not focus on to play out. Because you could put it in like play for unlimited of time, then it will finish all of the combinations. But for a practical reason, we don't do that. So what we do is that we set up criteria that we are happy with, and then we tweak those criteria depending on how that compares to how a player has done a playout. So today it takes like 5 hours for the criteria that we have now to play out. And I guess in the future we will learn better. Like we will have learnings like, okay, we can skip this and add this other criteria instead, because this is it will not bring any added value, but this other criteria might be more important for us. So we can talk afterwards if you didn't understand fully the answer. But this is like on a high generic level. How does it?
Carlo.
Hi.
Hi.
Did you maybe develop any tool to see code coverage or probably also data coverage when bot runs?
We have not looked at that yet.
Okay.
It has not been of any interest at the moment. So I guess that's one of those to-dos to explore that area and see if that brings an added value to the. But the thing that we are most interested now is to like, how can it mimic a normal player's playout? So that's what we're trying to learn. How can we tweak the bot so that it plays as our users does the playout?
And second part, I didn't get where does this bot run? Is it on mobile device?
No, it runs on a normal PC. So it runs on the code. Like what you do is that you build a special version of the game where the bot are like triggering the actions and recording the playout.
And you mentioned that also to do is headless mode for
Yes.
your bot.
Yes, you need to run it in headless mode for speed reasons. Because if you do like with a GUI, a playout might take like say 5 minutes if you have like a difficult level. But headless mode, you might run it in like 5 seconds.
So you have headless mode.
Yeah, in headless mode. So
Okay.
I would advise you to have support in your application to be able to run it without needing to draw the GUI.
Okay, thank you.
You should simulate that in the logic.
Okay, we've got one more back here.
I got 2 questions. The first one is who owns the bots in King?
Who owns the bot in King or in the team?
Like who is it the data scientist team or the
No.
developers?
So what we have done at King is we have formed a bot team. And what they do, they go to the different teams and help them out getting started with this bot thing.
And my second question is, you listed there are several roles of QA people in the team, and one of them is the quick regression team. What do they do then if we have the bots?
Can you repeat the last one question? What do the regression teams?
Yeah, there is a role called QRT, the quick
Yeah.
regression testers.
Yeah.
So what do they do? What's the job scope?
So what they do today is that they run the regression test team. They test the games manually today, but I guess in the future they will. We'll see where we'll end up. They might be the one that owning the bots in the future, and they're like helped by the developers to run them. That's one solution that they can do, and of course this is promising, but still we need like manual testing. So I don't think we will, get rid of them totally. So this is more like I guess a tool, complementing them to do the testing. So we'll see. We'll see where it will bring us.
Any more cards? One more up here.
Thank you. Is this all homegrown? Are there any open source projects that you used in doing this?
We looked at the market to see if there are any generic tools and stuff like that. And we didn't find any tools that we felt like were suitable for us. So and also like we like to be in control of what we're doing. So we are like we like the culture at King are that we try to build it ourselves, especially when we have this huge amount of users, because they create a lot of data that most tools out there doesn't support. So you really usually need to have custom. It's more pain to have a third-party tool than creating the tool yourself and being in control of the tools yourselves. At least for us.
Natalie.
You mentioned that you have a team of exploratory testers that are available to the teams. What kinds of situations will cause a team to go, oh, we need a ninja?
It could be like an example could be, let's say that we have made a bad release, and then there might be that tricky bug to reproduce. Then we can just we want 10 or 20 more testers that look into this to try to reproduce this bug. So that's where they really bring a really great value. Or if a team are busy with one thing, they can offload doing other stuff that needs to be done. So it's really good to have that as a buffer in your development process. So if you have the resources to be able to do that, I can recommend to have a pool of that. The same thing will go with the QRT teams. Some companies, they outsource the testing, but in our case, I think it's unpractical to outsource testing. So we have like an insourced solution where if there are any issues, we can address it immediately. We don't have to wait for external party to we're not dependent on that. But that's also like a resource issue. Then you need to have the resource to be able to do that. And another thing with the QA, like I mentioned, it's a good in-channel for QA people that want to get into the industry and have QA as a career path. It's a good place to start doing the basic work, and then you can see who has talent for it, and also people can try it out and see if they're interested in that area. So that has been a really good. It's been worked very well for us as an in-channel for QA people.
Anyone else? Okay, the stack is empty. Thank you very much.
Thank you.